I'm gonna record this. All right, so here I am. Sorry I couldn't be in class today as a primary caretaker and haven't been exposed. Even though I'm not feeling effects, I don't want to take any chance to pass it to you guys. Fortunately, one of your classmates have shown up so far. So I'm gonna, oh, there we go. There's more. Oh, so I will be doing the lecture. I was wondering if nobody would show up. I've never had that happen in a Zoom that was scheduled for reals. Okay, so I am going to share my screen. I am recording this. I'm going to make it go away so I can't see me. It is being recorded. I'm not going to forget, I promise. Control Shift Alt H, and our controls are out of the way. Here we go. So let's talk about section 8.3. And I'm only going to do one section today. I considered doing two, but maybe I'll do two on Thursday. We'll talk about it. We'll see. Basically, I'll talk about it and you'll listen, but we'll see. So 8.3 is all about probability and probability models. And everything from chapter 7 to chapter 8, they all build on each other. So make sure as you're doing the homework, you do them in order. It's going to make it a lot easier to understand. Even if I have to give you extensions, try to do them in order so that it's easier to do the homework that comes later. A probability distribution is an assignment of a number P of SI. So that's the probability. This P stands for probability. Mathematicians are not creative. Of SI to each outcome of a finite sample space S, where these little SIs are the elements of the set. Now, these probabilities have to satisfy two main conditions. Every little probability has to be between 0 and 1. 0 is an impossible event, and 1 is called a certain event. And that's between 0% and 100%. But also, not only are each of them only between 0 and 1, when you add all of them up from the entire sample set, right, all of the probabilities have to give you 1, a 100% chance that something in that set happens. All right, so probabilities are between 0 and 1. Each individual probability of a set of the sample space has to add to 1. All right, so we find the probability of an event E, written P of E, probability of E, by adding up the probabilities of the outcomes in E. And here we see the impossible event. The empty set event is always impossible since something has to happen, right? You flip a coin. It's not like the movies and it's just going to like stay flipping in the air forever while superheroes come and do stuff. It has to come back down. It has to land somehow. So the empty set's not possible. The coin lands. Gravity actually happens. A probability model for a particular experiment is a probability distribution that predicts the relative frequency. So, we're going back to 8.2 there, of each outcome if the experiment is performed a large number of times. This is called the law of large numbers, essentially, large number of times. Moving on, to find the probability in E, we count the number of ways E could happen divided by the number of things in the sample space. That union rule of counting that we had in 7.2 probably carries over, maybe 8.1, carries over for probabilities. Probability of a union, you add the individual probabilities and then you subtract that intersection, because remember we've counted that overlap twice. If the intersection is empty, so they have nothing in common, we call them mutually exclusive. And a couple of principles. Here we see one with what is that? Complement. The probability of A complement is 1 minus the probability of A. All right, we'll come back to this as needed, but let's just start walking through some of the problems first of all. So problems 1 and 2 are very, very similar, like super similar. I think the only difference is the color of these and the numbers, of course. Okay, so complete the following probability distribution table and then calculate the stated probabilities. So what I know is that when I add all of these up, it should end up being 1. So I'm going to add 0.4, 0.07, 0.4. I'm going to write it correctly. That 0 goes somewhere else. And I'm going to call this X for right now because I don't know what it is. And as a mathematician, I use X's for unknowns. So when I add up all 5 of these, it should equal 1. So let's see. So this is 0.47 plus 0.43 plus X. 47 plus 43, that's 80, 90. 0.90 plus X equals 1. X equals 1 minus 0.90. So our X value will be 0.10. And you can call it 0.1 because the 0.4 just has 1 decimal. But I left this at 10 because we had 2 decimals here. So either one will be good. Now, once you get this probability distribution filled in and you get that one right, so enter, make sure you got that one right, because all of these are building on this table. So the probability of A, C, and E. Well, A is 0.4, C is 0.4, and E is 0.1. So that's 0.4, 0.8, 0.9. So we'll just add up the individual probabilities. And that's what one of those first lines on the first page of notes was saying. Probability of E union F, where E and F are that way. So remember the union rule. So this is the probability of E plus the probability of F minus the probability of their intersection. All right, so so we already know that the probability of ACE is 0.9. ACE, that's 0.9. F is BCE. Well, BCE is 0.07 plus 0.4 plus 0.1. B, C, and E. So that's 4 and 1 make 5, so that's 0.57 minus, now we need to figure out what these two have in common. Throw down some minor orange. It looks like they have some CE in common. So in common, the C and the E, that's going to be 0.5. Okay. The C and the E are what are in the intersection of the sets E and F. That was something that we talked about in chapter 7, all fields. So the probability is the probability of C and E, those ones that overlap, that intersect, that they have in common. And C and E added together give me 0.5. So when I do this calculation, I'm going to actually do this part first. 0.57 minus 0.5 is 0.07 plus the 9. So it's 0.97. All right. Remember, this is all new, totally new stuff. So if it's not immediately obvious, it's totally okay. All right, so what did we know in part B? We know that the probability of E is 0.9. But we know also that E and everything not in E has to add up to be the total. So the probability of the complement is 1 minus 0.90. Oh, we kind of had something going on there earlier, very similar. So the probability of event E, capital E, which is different than lowercase e, probability of capital event E is 0.9. So the probability of the complement of that, the opposite of that, if it's a 90% chance E happens, it's going to be only a 10% chance that E doesn't happen. And it turns out, how handy is this? We already have the probability of E intersect F. So let's not do it again. We already have that answer. there's no need to continue to compute, right? Look back at the work you've already done. Angela, question.
Quick question. How did you, I'm a little confused, way to the back on when you added 0.4, 0.7, 0.4, and 0.3, how did you get 0.43?
I added these two. I added these two and got that value. And these two to get that value. I did two at a time in my head instead of pulling out a calculator.
Oh, okay. Okay, that makes sense. And then you did the same thing when in part B?
Yeah.
Okay.
What I really should have done was not be lazy, and I should have said something like 0.9 plus 0.57 minus 0.5.
No.
So yeah, I did it in my head, but you should not trust my head right now. That's a much better answer.
Okay, thank you.
You're welcome. Anybody else? I'm sorry it took me so long to get to that. All right. Good. I need to make me go away. That's what I need. Okay. Fantastic. Let's keep moving on. All right. So number 2 is exactly like this one. Exactly like this. Number 3. Calculate the modeled probability P of E using the given information. Assume that all outcomes are equally likely. Now, modeled, this is another way of saying, even though the math says this should happen, it doesn't always happen like this. This is mathematical probability, theoretical probability. There's not a lot of emphasis that we really need on this. Obviously, we're doing the math because it's a math class. Okay. Using the given information, remember I breezed through the probability of event E is the number of ways E can happen divided by the total number in the sample space. All outcomes are equally likely. The number in the sample space, 1, 2, 3, 4, 5. I do not care what those 5 items are. They could be 5 cars, they could be 5 people, they could be 5 stooges. 1, 3, 5, 7, 9, those look good. It doesn't matter. I only care about how many. And along with that, my event E, I see there are 3 of those. And so when we put these together, we have just calculated the modeled probability. 3/5, you can also call this 0.6, whichever you prefer. It will accept both answers. Let me show you. Number 3, 3/5. Come on, there we go. You can also put 0.6. Although after you got it right the first time, I don't know why you would do that. But I know some of you are overachievers. And I know that some of you are going to want this problem to be harder. But that's it. Stop. Let it be easy. Let it just be putting numbers together. Okay. An experiment is given together with an event. So 4 coins are tossed. That's my sample space. The result is more tails than heads is my event. So I want to find the modeled probability of the event, assuming that the coins are distinguishable and fair, and what is observed are the faces uppermost. So we're not using 2-headed coins or anything like that. One's a quarter, one's a nickel. We could tell them apart. So what we know is when we have 4 coins are tossed, there's an I in there somewhere. 4 coins, there is, right, 4 different things are going to happen. So we have heads or tails for the first one, and then, so we multiply. Heads or tails for the second, and then heads or tails for the third, and then heads or tails for the fourth. This is a lot like those true false questions that we talked about with Professor Easy and Professor Tough or whatever. So two options when you flip a coin, you flip it 4 times. 2 times 2 is 4, times 2 is 8, times 2 is 16. So this will be the number in the sample space. Now, as we're looking at what's in the sample space, I don't want to write all 16 of these things down, but I could if I had to. It looks like I might have to. So I'm going to have a nightmare about this problem. Okay, here we go. They're all 4 heads. Or that last one's a tails. So what I'm going to do is I'm going to leave this first thing heads 1, 2, 3, 4, 5, 6, 7, half the time, and half the time that first one is tails. 1, 2, 3, 4, 5, 6, 7, 8. So that's just first coin. Now I'm going to leave the second coin at heads. Oh yeah, and this is just exactly the same thing, only the first coin was tails. Heads, heads, tails, heads. So I went back to the original. Now I've changed this head to a tail. And then I'll change that last one. Not pi, it's TT. And then I'll go back to the original. I changed that to a tail. I've changed that to a tail. Now this one becomes a tail. Back to heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. Having an organized way of writing your list is super helpful. It's also super helpful to not talk while you write it. It's also super helpful to like have this written down or look it up online too. Because anyway, there you go. There it is. The result is more tails than heads. So I have 4. I have 1. I have 1. They're equal number. I want more tails. So there's 3 tails. I mean 2. That's not 1. That has more tails than heads. That has more tails than heads. That has more tails than heads. All right, so this is 0 tails, 1 tail, 1 tail, 2. Keep saying that often enough and it really starts to sound weird in your head. Probably out loud too. Missed that one. Okay, so not this one. And look, I have an eraser and I just decided to put an X on it. Come on, there we go. Don't be lazy. 1, 2, 3, 4, 5. 5 ways. So in order to write my probability, this will be 5 out of 16. The hardest part was writing these down to figure out how many more heads than tails are we. But now that it's all written out for you, we might use this a little bit as we do some other problems. The first one we're going to look at, Angela, is this Alvina? You prefer Alvina, don't you? Is your hand up still or we good?
Oh, no, I haven't raised it.
Okay.
Oh, sorry. I just lowered it.
No worries. That way I cannot look at me. Okay. Are we good? Are we all good here? Let's put number 6 up. All right, I'm gonna make that go away in case you're still writing and in case we need to look at this. Number 6 together. Tutorial exercise. And it's gonna lead us straight into number 7, which we're gonna do as well. Okay. A die is weighted in such a way that each of 1 and 2 is 8 times as likely to come up as each of the other numbers. Okay. So I'm going to write something down here. 1 and 2, 8 times as likely That's 3 through 6, right? And it's a die. We're assuming 6-sided die unless they say otherwise. Okay, so we're going to find the probability distribution associated with this die. The probability of each outcome is unknown. So the first step is to use the properties of probability distributions. Whoa, that was hard for me. To write an equation that we can solve for the probability of one or more of the outcomes. We're going to let P of 3 be X. But keep in mind, 4, 5, and 6 have the same probability as 3 does. So those will just be X. They're all the same. All right. However, 1 and 2 are 8 times as likely. 8 times as likely to come up as 4, 5, and 6. So 1 and 2 are going to be 8X, whereas 4, 5, and 6 are going to be X. So it kind of gives you the answer for these blanks in these ones, right? The probability of 1 is 8X. So it tells you the answer if you just look down. But, you know, we figured it out anyway because you're smart people. All right, step 2. We found the probability distribution for the die in terms of an unknown X. Recall the probability property says that they all have to add up to be 1. In other words, probabilities of all of the outcomes, rolling any of them, will add to 1. So the probability of 8X plus another 8X, so 8X plus 8X plus X plus X plus X plus X equals 1. And it really just wants us to add all of these up. And that's a stupid blank for you to fill in. And it's not stupid. Whoever wrote this, since I'm putting this on YouTube, that was a great problem. It just seems a little odd. We're adding this up. 8 and 8 make 16, 17, 18, 19, and 20. So we will have 20 X's equals 1, and X is equal to 1/20th. I can put 1/20th, and it's still going to give me a good answer, even if it is 0.05. And you see here, the answer 0.05 will be a lot easier for us to work with. But at least I didn't, you know, mess up my decimal. I typed in a fraction. Okay. All right. We found the probability distribution for the die in terms of an unknown X. We also found the X is 0.05. So 8X is 8 times 0.05. Let's not trust my brain on this one. 8 times 0.05 is 0.4. Sirens outside, something going down in the big city of Cruces. Expect my dogs to go nuts here in a minute. Use the value of X to write the complete probability distribution. So look, I mean, they even gave us what 8X is. Put in a decimal. 0.4, 0.05, and I'm going to make them match exactly how the other ones are written so that I don't have to worry about, did I get enough decimals? Did I put it right? I'm going to make them all match. All right, last step. We previously found the probability distribution for the die. Next, we will compute the probability of rolling an odd number, which can be written in probability notation as the probability of rolling a 1, 3, or 5. Recall that the probability distributions for an event E, the probability of E, we just add up all of these. So we can find the probability of events 1, 3, and 5 by finding the probability of 1, which is 0.4, the probability of 3, which is 0.05, and the probability of 5, which is also 0.05. And when we add those up, .4 plus 0.05 plus 0.05, we end up with half. Which, I mean, we kind of knew. Because between 1 and 2, right, odds and evens, and everything else is split, half the time it's going to be odd. Okay, I'm going to submit this. It would be different if the die 1 and 3 were weighted heavier, then odds wouldn't be a 50%. But since everything has a balance in that equation, that one, it turned out to be 50%. And we got 14 points out of that. And so I want to definitely walk through it with you because that's a large amount of points and we like points. All right. So now we're going to do it again. A die, and without walking step by step through it. A die is weighted so that each of 2, 4, and 6 is twice as likely to come up as 2, 4, and 6. Oh, my goodness. Twice as likely to come up as 1, 3, and 5. So we want to find the probability distribution. So we'll do exactly like we did before, right? If these are all X, then the evens will be 2X. And we know that all of these will add up to be 1. That's an ugly 2X, but it is a 2X. So 1, 2, 3, 4, 5, 6, 7, 8, 9, X equals 1. X equals 1/9. So 1/9, 2/9, 1/9, 2/9, and so on. Twice as likely, right? 2/9 is twice as big as 1/9. And when we add them all up, there's a total of 9 possibilities. One way I like to think about that for me to see it is we could have 1, 2 is twice as likely, 3, 4 is twice as likely, 5, and 6 is twice as likely. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes. 1 is one of those 9 outcomes. 2 is 2 of those 9 outcomes. 3 is 1 of those 9 outcomes. And we can find it that way as well. But using the step through it that we just did, number 7, we can also use variables. So whichever way makes more sense to you is the way that you should go about it. So now what's the probability of rolling less than a 3? Less than a 3 is these. So not equal to, just less than. That will be 1/9 plus 2/9. And you all remember, now that I'm about to say it all out loud, that we add the numerators, leave the denominator alone, and we will always reduce our fractions. Keep in mind, I'm going to make this in red. Yep, I knew they were going to go on. One-ninth is the answer, not 0.11 or even 111. 1/3, not 0.33. Exact versus rounded. We always want exact values on WebAssign unless it tells you how to round. It doesn't tell us how many decimals, and if it doesn't tell us how many decimals, it wants a fraction. And it's very, very particular about that. All right, we doing okay? Fantastic. No answer is as good as an answer. Okay. So we use the given information to find the indicated probability. A intersect B is empty set. So this little piece of information here tells me that the probability of A intersect B is 0. And I have to scroll quite a bit to get to this. Oh, it's not too bad. Oh, it is too bad. Way up here. The probability of the empty set is 0. Also, while I'm here, okay, I can't point it out. Mutually exclusive, when the intersection is the empty set, it's just the sum of the probabilities. But notice we have the probability of a union. We have these, both of these rules are addition principle. Let's take it back down to where we were. Here's what we know. We know that the probability of A union B is equal to the probability of A plus the probability of B. Because the intersection is 0, it doesn't matter if I put it on or not. If I want to, it's just not necessary because it's 0, because these are mutually exclusive. So I'm going to substitute for what I know. I'm going to put an X for what I don't. Oh, interesting when I subtract. Probability of A is also 0. That seems weird to me. So I want to pull this up. Lots of steps. I get 0. Oh, wait a minute. That's not the right problem. You get probability of A is 0 on number 9. And I want to make sure that we're right. Because frequently when I get an answer of 0, my natural instinct is, oh, that can't be right. Or why would it be 0? But it is just as valid as any other number. So yeah, use your formula, take it slow, take it simple, listen to my dogs bark, all those good things in life. All right, number 12. Number 12 is the last problem on the homework. And as you know, that means it's probably going to be extra challenging. And probably, as you've noticed, I don't do a lot of those problems just because I like to see you put yourself out there and attempt these. But today we're going to do it. The following chart shows the approximate or total number of subprime home mortgages in a state in November of 2008. This is when what is going on here? There we go. This is when the housing bubble burst. Yeah, you can hear the little chihuahua, huh? Little devil. Hold on. Knock it off. Go outside. Yeah, I couldn't find my mute button, so yeah. Okay, here we are. We're good. Bubble burst. Housing market collapsed. People went into debt and they're still trying to get out of it. The 4 categories are mutually exclusive. So if they are current, they are not in any of these. If they have already been repossessed, they are not considered in foreclosure. They've already processed out of that. So none of them overlap. Find a probability. All right, so we're looking at a fraction. Every time it says probability, we're looking for a fraction. Or a decimal less than 1. That a randomly selected subprime mortgage in the state during November of 2008 was neither in foreclosure nor repossessed. All right, so when I randomly pick, I don't want those two. So what I do want for A is I want all of the current, I'm going to write that number correctly, and past due. And those are the only possibilities, right? Find the probability that a randomly selected subprime mortgage in the state during November 2008 was not in foreclosure nor repossessed. So it's got to be these two. And we know our whole total over here is always going to be our denominator. Always be our denominator because that's the total, that's the size of the sample space. So yet again, not trusting my brain to be completely accurate. Let's clear that out. 106, 330 plus 51, 310. I read those numbers out loud, but remember to use the numbers on your problem, not mine, before you write this in. 157,640 over 172,082. 2 decimal places. Oh, nice. Cool. Let's bring back that calculator. And let's divide that by 172,082. 91607. 2 decimal places. That 6 tells me that I'm going to call this 0.92. All right, so I'm going to take off this circle. That's not our answer. All right. Checking in. We're good. We're good. All right. What's the probability that a randomly selected subprime mortgage in the state during November 2008 was not current? So not this one. So for part B, give ourselves a little space here. Not current means it was past due, or, so we're going to add in foreclosure, or, remember, or is a union, it's always an add, repossessed. Out of all of the total, right? So, or we add, bring out the calculator, we have, I'm not going to say them out loud. $65,750. And then we're going to find the decimal for that. So we'll divide it again by our total. I'm going to make sure that I messed this one up. That's not an 8.2. I divided wrong and nobody told me. I'm guessing it doesn't change that much. I got to use the right number. I'm going to fix that. Let me finish this one first. 0.382. 2 decimal places, so this should be 0.38. Let me erase this. This is the wrong number because Tuesday can't concentrate like ever. Where are we going here? We have start a new problem. 157,640 divided by 172,080. Yeah, it's still that that 7 changes to an 8, but that's all right. It was fortunately not big enough mistake that I have to worry about it. Okay, and that, my friends, is all the problems that I had prepared to talk about. Now we do have time if you want to ask questions on 8.1 or 8.2. And I'm going to save this. I did record. I recorded. I'm so excited about that. No, it's because I like to hear my voice. It's because I screwed up yesterday on an important problem that I wanted all the students to be able to see. What we can do now is this. You know, any questions that you guys ask me on homework, just let me know. Hey, I'd like to see this in class instead of just like an answer back. I can always add those questions to the end of the lecture and give you help that way. I haven't seen a lot of questions from some of you here and there, but not a lot of questions lately. And I haven't been looking, I haven't been keeping tabs on you. But I'm assuming that you're keeping up with your homework, even if through extensions. I think what we're going to do is this. On Thursday, I'm going to lecture 8.4 and 8.5. Both sections. And then we're finished with the lectures. And then Tuesday, a week from today, which is the Tuesday of Thanksgiving week, I'm gonna have online class that's drop-in only. It's like office hours, but only for you guys. So I won't have anything planned, but I'll be here in case you have questions over any of the homework. I'm gonna make sure you have access to the exam 3 and final exam reviews at that time. And then probably I'll be back on campus after Thanksgiving for that final week of review. So we won't have any more lecture after this week, official lecture. You'll still have time to do your homework, and then we'll start reviewing for both exam 3 and the final kind of at the same time from here forward. Does that sound cool with everybody? Does that work for you guys? The chat, more in the chat. I always forget about the chat. This is 8.3. Thank you all for answering that. What were the last two answers, Emily, on which one?
On the one that's worth 14 points. The
Gotcha. Yeah.
yeah.
There you go.
Okay, thank you.
You're welcome. I'm sorry, I forget about the chat all the time. I don't know. And, you know.
Ms. Johnson, for 8.1, could you go over number? Give me a second. Yeah, could you go over number 3 and number 7, please?
8.1, number 3, and number 7.
Yes.
Uh-oh. I have to get an extension. Do you guys need extensions on that one too? It was due yesterday.
Yes.
I can extend it to Wednesday if you guys would like it.
Okay, thank you.
You're welcome. Let's make it Thursday because mine gave me till Thursday, so that's cool. Here we go. And I remember to give ourselves some more paper down here, so I'm going to. This one I'm not really going to write, but I'm going to. My screen's on, right? No. I'm not sharing my screen, huh? Yeah. Look at me catching it before it happens. All right. Here we go. Instead of writing it, we're just going to talk through number 3, and then we'll look at number 7. That'll be a different story. So you're considering purchasing either a domestic car, an imported car, a van, an antique car, or an antique truck. So this, everything before the semicolon is going to be your sample space. So everything that's listed here, you want to click here. Imported car, a domestic truck? No. Okay, I have to think about it really simply. A domestic car, an imported car, a van, antique car, or an antique truck. All right, so my sample space will be everything that's listed. And now my event is I don't buy a car. So out of these, the imported car, domestic car, antique car, we're not going to have those. But domestic and imported trucks were not even in our list, so we can't think of those either. So van and antique truck are the only options of the ones checked up here that are not a car. Fingers crossed and submit. Does that make sense?
Okay, so you said that because I know it says like at the end of the question it says you do not buy a car. So at first I was thinking like all the cars are not going to be checked, but the trucks are going to be checked off.
But not all of the trucks are in our original list, so we can't include those.
Oh. Okay. Thank you.
You're welcome. Number 7 looks like we should write something down. No, come on, come on. There we go. 8.1. Yeah, right. Number 7, suppose 2 dice, one red and one green, are rolled. So this tells us they are distinguishable. And we know that there are 6 outcomes on the first one, 6 outcomes on the second die, for a total of 36 outcomes. Okay, so the red die shows a 4. Okay, so set A is the red die shows a 4. So it's going to be a 4 with a 1, a 4 with a 2, 4 with a 3, 4, 5, and 6. And the green die could be anything else at all. Okay, so that's my set A. Whatever, I should have a little squiggly after. B, the numbers add to 5. So if I'm looking at B, how do we add to 5 using 2 dice? We could have 1 and 4, 2 and 3, 3 and 2, 4 and 1. Because they're different, I could have written these in red and green, but we get the Christmas message here. It's red and green die, they're different. This wants the numbers do not add up to 5. Well, that's the opposite of B. The numbers do add to 5. So that happens to be just the opposite. What might they say instead? I'm going to bring us back over here because I did a whole bunch of nonsense that wasn't helpful.
Quick question, where did you get the 6 from?
These ones?
Yes.
Because if the red die shows a 4, it doesn't say what the green dice is. So the green die could be any of the 6 numbers. But it turns out they're not helpful in this problem.
No, I meant like where, because I noticed you multiply, you did 6 times 6 was 36 outcomes.
6 sides on a die. When you roll a dice, you could have the numbers 1 through 6.
Oh.
And then the numbers 1 through 6. I can't make one in there. Yeah, it's just because there's 6 sides to a die, and that's why. That's why we use 2 for coins, 2 sides, and 6 sides for a die.
Okay.
So how many elements does it contain? We see here that we have 4 that are in B. 36 minus 4 is 32, not in B. And so that would be 32 elements. And after what we talked about today, we now know that probability of not rolling a 5 is 32 divided by 36. But that's not part of 8.1. That's just part of what we did today. So a later thing that you might see. Other questions?
Can you do number 2?
Same assignment?
Yes.
Yeah, these ones are tricky, huh? Yeah. Okay. Consider the following. Assume that what is observed are the numbers face up. Indistinguishable dice are rolled, so they're the same. 2 white dice in the game of Monopoly. So we know that there's 21 outcomes for indistinguishable dice. And probably the easiest way I can show that to you is on my website at our class. I have this fancy handout called Dice Coins Cards that I need to update now that we live in a colorful world and not handouts of black and white. This whole chart is distinguishable, and this is where we see all 36 of them. For indistinguishable, consider only the portion containing the bold values and above. So here we have 6 plus 5 makes 11, plus 4, 11 and 4 makes 15, plus 3 makes 18, 19, 20, 21 total outcomes. So that's how I know that there's 21 outcomes. You know it partially because I told you so. But we can also use this chart to come up with the possibilities. Now, as I'm looking at this chart, is there ever a time when one of the dice can show a 7? No, only when we add do we get a 7. So I'm not going to choose any answer that has a 7. 1, 2, 3, 4, 5, 6 with 1, yes. With a 7, no. With a 7, no. 5, 5, and 5, 6. Let's look. See how these two are the only ones, bold and over? And I do that with each one. I'm going to do 2, starts with 2 through 6. 4 starts with 4. 3 starts with 3. And 6 only has 6. So there's 6 of them with 1. 1, 2, 3, 4, 5 of them with 2. 4 of them with 3, 3 of them with 4, 2, and then 1. And I feel pretty confident about that. That was challenging, don't get me wrong. But this chart, super helpful. And now there's a link to it if you want. Okay, I see a hand raised. Sorry, not there. Esmeralda, right?
Yes.
All right, what's up?
Can you explain how you got the answers for the second part of 8 and 9? It's because when I watched the video, I like did what you did, but it says my answer is wrong, so I don't know.
Okay, absolutely, absolutely. I just realized the numbers add to 6. Out of these options, just the ones that we have highlighted, which ones add to 6? 3, 3, 2, 4, and 1, 5. 3, 3, 2, 4, and 1, 5. So there's 3 of them. 3, 3, 2, 4, and 1, 5. And I hate that problem because it's square and you think, hey, that's going to be, oh, yeah, we'll do 8, 9 again for sure. You think to yourself, hey, that's going to be a multiple select, but there was only one. Let me show that to you again as I get ready for this problem. So we are still on 8.1, number 8. All right, now I'm going to jump down. There we go. Pablo randomly picks 4 marbles from a bag of 10. So we have 10 total, and we want 4. Okay, we have 10 marbles, and we always have to account for all 10 of them. And when we grab a handful, we want 4. And our combinations, if we're just randomly grabbing and order doesn't matter, it's always combinations of have, comma, want. So we ask ourselves, if he randomly picks 4 marbles from a bag of 10, how many outcomes are in this sample space? So it's not really part A, but I'm going to call it part A. That is, out of the 10 marbles, I want to randomly reach in and grab 4. This will be 10 factorial. This is from 7.4. 4 factorial over 10 minus 4 factorial. And I know a lot of you are screaming like, Tuesday, don't do this, just use the calculator. You're right. So when we write it out, this actually isn't that hard. 6 factorials cancel. The 4 and the 2 cancel the 8. 3 goes into 9 3 times. I am actually writing this exactly the same as I did on the previous notes. That's crazy. Okay, 30 times 7 is 210. So there are 210 different ways of grabbing just 4 random marbles from a bag of 10 marbles. But in part B, which is not really part B, but I'm going to call it part B, none are red. So remember, we have to account for all 10 of them at all times. So what I'm going to do is I'm going to look at the red, and I'm going to look at, and then not red. Red and then not red. So when I look at red, just the red marbles, I see that I have 5 red marbles. And remember, the combinations are always have, comma, want. But I want none of the red ones, so I want 0 red ones. But then, right, and then, so we multiply. How many are not red? Well, there are 3 green ones and 2 yellow ones, and those are not red. So 3 plus 2 makes 5 that are not red. And we want 4 of those because ultimately we're still trying to grab 4 marbles. We just don't want any red ones because we're marble colorists. And so we can find these individually. C of 5 comma 0 happens to be 1. In general, I'm just going to tell you now, C of n comma 0 is always going to be 1. If I have 5 mini Snickers bars on the table in front of me, and I want to choose 0, I don't want to eat any, the easiest way to do that, there's only one way, is you don't do it. All right, that's it. There's one way. This one, it turns out, is equal to 5. Because really, anytime you get C of n comma n minus 1, or whether you're choosing 1 or all except 1, you just get that number back. So this turns out to be 1 times 5, which is 5. And I'm going to say it again because we've already talked about 8.3. And what we'll start doing in 8.3 is it won't tell you that you need to find this. But in 8.3, we're going to start finding this denominator, and this is going to be our numerator. It's probably 8.4. And then we're going to put these fractions together. So a lot of what we do in 8.1 and 8.2 comes back at us. So I'm going to extend 8.1 homework so that you can all make sure you get some chances at doing better in 8.3. Number 9 should be pretty much the same. In this case, all are red. I'm just going to look at B. So I would look at all red and then, so multiply the others, which are not red, right? Because we know it's either E or E complement. They're either red or they're not red. So of the red ones, there are 6 red ones. We want to pick 5, and we want all of them to be red. And once we've handled the red, and then we have to take care of the others, the not red ones, there's a total of 11 marbles. 3 and 2, so 5 of them are not red. We're picking 5. We want them all to be red. We want no other colors. So this one also turns out to be fairly straightforward. But you'll want to write it down, and it's using these rules that I was able to find that. You'll want to write it down to solve these, to make sure that you understand it as well. Any other questions? All right, right here while you're watching. Get that extension going. Where did I say Thursday? 18. Oh, not 118. I don't know what date that is. There we go. Well, that's ridiculous. Why would you have 8.2 due before that? Hold up. Yeah, so let's make this one also due on the 18th because it was the same lecture day. And then the next day for the quiz. And then I'm pretty happy with the rest of those dates. Make sure I do the same thing so that everybody has the same chance. $18, $18, $19. Yeah, yep, I'm happy with that. Okay, I'm going to stop sharing my screen. I'm really done talking. Anybody else have any questions?